Welcome back to How to Program. Just a warning, if you're on this channel for the first time, this show is best viewed in order. We recommend you start with the first episode and go from there because the concepts build one upon the next. So if you have not seen the previous episodes, you can click on our channel name and go to our channel to start with episode 1. This episode is episode 6, binary, and we're going to talk about how to represent negative numbers, which are numbers that are less than 0. Now, in our last episode, we had a little exercise for you on how to add binary numbers, and so these are the results. You can pause the video and check if you ran this at home and see if you got the correct answer. All right, so let's talk about negative numbers and signs. The sign, or a sign, is a symbol which says whether the number is positive, which means the number is greater than 0, or negative, which means the number is less than 0. A signed binary number is a binary number which can represent both positive and negative numbers because it has a sign, and so we say it is signed. An unsigned binary number is a number which does not have a sign and can only represent positive, 0 or greater, numbers. So far, we've only talked about unsigned numbers without really calling them unsigned, but we've only talked about positive numbers. And so now we're going to see how we could potentially represent numbers that are negative. So I'm going to show you 3 different options for how to do this and how we could potentially do this. And then we'll see which option actually ends up getting used today in computers. But going through these options is going to show you why the option that ultimately gets picked is the best one, I will say. So let's take a step back and say we were imagining how to represent in a binary way a sign, a positive or negative. Well, positive or negative is just 2 values, and so we can use just a single bit, a single binary number, 0 or 1, to represent that sign. And so maybe the first option we would say is just, well, we're just going to use the first bit, the one all the way to the left of the number. We're going to say that bit means the sign. So 0 on that bit would mean positive, and 1 on that bit would mean negative. That means if that bit is 1, then the rest of the bits represent the actual number, and the number would be negative because the sign bit, this first bit we now call the sign bit, would be 1. So at this point, that bit doesn't affect the number anymore. It's not part of the number apart from just saying which sign it is, whether it's positive or negative. And so the rest of the bits would be called the magnitude, which is, how much. So the actual number is basically what we would be representing at that point. So if we did this, we're going to work with 3 bits. I know this is a little bit odd, and there's not really a place in a real computer where you're going to have 3 bits, but this is going to make things easier because they will all fit very easily with very few values, and it's good to just have few values to start this out. So let's look at how this would work with 3 bits. So remember, the first bit now represents the sign, and the last 2 bits now represent the actual number. So starting at binary value 0, 0, 0, we go up, and you can see the decimal value goes up all the way to 0, 1, 1, which represents 3. So far, this is similar to what we've seen. Now, when we go to 1, 0, 0, the 1 now means negative, and then the 0, 0 is the actual number, so it's a negative 0. That's kind of weird, but that's okay. That's fine. That's what we said. So it's just another way of saying 0 now in this system. And then we keep going. So 1, 0, 1 would be negative 1. 1, 1, 0 would be negative 2 because 1, 0 on the right means 2. And the 1 on the left means negative. So that now means negative 2 in this system. And then 1, 1, 1 would mean negative 3 in this particular system. Let's take a look at how this option works. It has some problems. Like, for example, 0 is there twice. You saw the 0 and then you saw the negative 0. That's kind of weird because when we're checking whether both numbers, like 2 numbers, are equal to each other, we now need to know, like, oh, well, but 0 can be represented with all zeros or 1 and then all zeros. So now we need now to check for this. You know what I mean? We need to check, like, and do a special thing for that. So that's not the greatest. We're also, with 8 possible values, with 3 bits, we can represent 8 possible values. We're wasting one value here. We're wasting this -0, which is just kind of a weird value. So it's, this is not the greatest. And then it's also really hard to actually implement this, like to put this into effect in hardware when we're designing the little circuits on the circuit board. It's actually really hard to do it this way. So this is not necessarily the best option. Let's take a look at another option. Now, let's say we're totally changing our direction here. And let's say, okay, well, this whole sign bit thing, that didn't work the greatest. So we're going to say, in order to get a negative number, we just reverse all the bits. All the ones become zeros, all the zeros become ones. And that now becomes the negative value for that positive number. This actually has a name. It's called ones complement, because we're just basically flipping one time, and that's what it's called. And so if we did this, now let's look at our table of possible values. So we go from 0, 1, 2 to 3 on the left side here. And these are the positive numbers. So these don't get flipped. These are just normal binary from 0, 0, 0 to all the way to 0, 1, 1. And that's from 0 to 3. And then on the right-hand side, we have their flipped values. So now when we take 0 and we flip its value, we get ones complement for that number. We get all ones, and that now is -0. -0 again. Okay, well, that's fine. Let's keep going. So for 1, we want -1. So now we say -1 is the flipped bits of 0, 0, 1, and that's 1, 1, 0. That's one's complement for that. That's -1, 1, 1, 0. Good. Now we take 2. We say, well, 2 is 0, 1, 0. So -2 is going to be that binary number flipped. So that's 1, 0, 1. So that's -2 is 1, 0, 1 in this system. Good, and we do the same for 3. 0, 1, 1 becomes 1, 0, 0 when its bits are flipped, and that's -3. Okay. So if we put all this together on the same sort of table in order, in binary order of the ones and zeros, this is what we end up with. The values go from 0, 1, 2, and 3, and then they reverse. They go 3, -2, -1, -0. Okay, that sounds so bad, but there's still this -0 here. And now this -0 is weird because now -0 is all ones and our actual zeros all zeros. That's not the greatest. We're still have this -0 value, which requires special comparison. And then, this is easier to implement in hardware, but it can still cause some issues. And we're still wasting this -0 value. Okay, well, maybe there's a better option. Now let's say we were crazy and we tried this option. We like this flip the bits option. So that's the first thing we're gonna do is we're gonna flip the bits, just like we did. And then we're gonna add a single binary 1. We're gonna do an actual addition. This is not just like put it on the left or right. Like we're gonna do an actual addition with adding a single 1 to every number. So we can call this 2's complement. And 2's complement would be take the binary number, flip its bits, add a single 1 through binary addition that we just saw in the previous episode. Like this is the actual binary addition of 1. And then we get a certain binary number, and that would be its 2's complement. Okay, let's see if we do this, what does this look like? Well, the first thing we're going to have to look at is 0. So if we take the binary value 0, it's 0, 0, 0. We flip the bits. The 1's complement becomes 1, 1, 1. We're going to add, through binary addition, a single 1 to that. And that is now 1, 0, 0, 0. It's a 4-bit number. It's not a 3-bit number. But we're in a 3-bit system. We said this system is 3 bits. That's what we're working with, 3 bits. So when the computer gets this particular thing happening, and that extra 1 on the left is there, it just gets dropped. It says, oh, you've got 4 bits while you're using a 3-bit system. So that leftmost 1 is just gone. It's in red here. You can see it. It just gets dropped, which means, oddly enough, that -0, the 2's complement value of 0, 0, 0, is also 0, 0, 0 in 3 bits. In the same number of bits that we started with, ends up being the same. Well, this is fantastic. Now we don't have a negative 0 anymore. We just have 0. 0 and 0. It's just 0. There's just one value for that. So that's great. Now let's look at the other values. So we take the value for 1, which is 0, 0, 1. Now we flip its bits. That becomes 1, 1, 0. That's the ones complement column in the middle here. And then we do a binary addition of 1 to that number. So we get 1, 1, 1. 1, 1, 1 becomes negative 1 in this 3-bit 2's complement system. Good. We do the same for 2. The minus 2 becomes 1, 1, 0. We do the same for 3. Minus 3 becomes 1, 0, 1. Okay, for 4, it's a little tricky here because if you look, let's do this one. So 4 is 1, 0, 0. We flip the bits. That becomes 0, 1, 1. To which we do a binary addition of 1. The 2's complement is 1, 0, 0. That turns out to be the exact same number we started with, which was 4. Okay, so that's a problem. But, okay, so there's a trick here because if you see, the leftmost bit is a 1. So if we take this idea of the sign bit again and just say, well, okay, we want the ones, the numbers that start with a 1 to be the negative numbers because we know the 1 means negative in the sign bit system that we used earlier. So we say, okay, we're gonna tie break because we could represent 4 and minus 4 as the same binary number, but we're gonna tie break because it starts with a 1. That's going to be a negative number, so that's going to be negative 4, right? Okay, so this gives us the actual following table. In our 3-bit system with a signed 3-bit system using 2's complement, that system that we saw to flip the bits and add 1, that's 2's complement. This is the values that you get. So it starts at 0, which is all zeros in binary. Then you go to 1, 2, 3. Then we hit minus 4 because that's what we decided. We're 1, 0, 0. We decide, okay, that's minus 4. Then 101 is minus 3. 110 is minus 2. All ones, 111, that's minus 1. So note, if you see the pattern, right? It reverses. So from the bottom, it starts minus 1 and goes up towards the middle of the table back up, right? If you're starting at the bottom of this table at minus 1 and you're going back up the rows here, like it goes all the way up back to minus 4. And then it starts 3 and then goes back down to 0. So it's kind of like a symmetry almost, like, you know, the things that it kind of looks the same on each side except for that minus 4, which does the tie break here, which is one more negative value. So there's one more negative value than there is positive values, as you can see. And this is always true. No matter how many bits you do, this pattern is going to be the same. The number which has all ones in binary is always going to be negative 1 in a 2's complement system. And all zeros is always going to be 0 as well in a 2's complement system. Now, there's some really good things about this system. For example, numbers represented in 2's complement can just be added together with no special step. And it just works. So this makes the implementation in hardware much easier because subtraction just becomes an addition of the 2's complement of the number you want to subtract. This is pretty cool. Let's take a look at how this actually works. So let's say we want to do an addition, and this fits within our 3 bits. We're going to add minus 3 and 3. So we have our table on the right. Minus 3 is 1, 0, 1. 3 is 0, 1, 1. Let's do the binary addition of that. Binary addition, we do all the carries and everything. We end up with a single 1 and 3 zeros. Same thing as earlier, because we're using a 3-bit system and we got 4 bits. We drop the leftmost bit. That red bit, that 1, just gets axed. And then we get our final number, and we get all zeros, which is 0. This is the correct answer, minus 3 plus 3, that ends up to 0. So this works as long as the numbers don't overflow the number of bits used. This means that we need more bits to represent the value we really should have gotten than the ones that we're using. We're using 3 bits, right? So if we want to represent a number that negative or positive, it doesn't matter, right? Like if the number isn't in this table for our 3-bit 2's complement system as the result, like if the result is not in the table, then it's not going to work. So let's look at an example of how this would not work. What if we add 2 and 3? Well, we know that's going to be 5, and we know 5 is not in the table, so this is going to be problematic, right? So if we add it together, what we get is a binary 1, 0, 1. You can pause and do the math, but this is the number in red here. In our system, this would be -3, which is the wrong answer. So how do we know that we made a mistake here or that something went wrong? We can detect this because the first two numbers, the 2 and the 3, in binary both start with a 0. We know that the sign bit 0 means positive. So we added two positive numbers, and we got a negative number because it starts with a 1. Well, this is easy. We can see that if we add two positive numbers and we get a negative number, we know we got something wrong. This is a wrong result, right? So we know we overflowed the amount of space that we're using. And this is very easy to look. You can see also in the table that all the binary numbers that start with 0 are positive, except for 0, which is, just kind of an odd number in general. But it's, it's fine. And then all the numbers that start with a 1 in binary are all the negative numbers. So this is very easy. We can detect when there's an error like this. And this is called overflow because we required more bits to represent the real result we wanted than we had in our system. What about, we can try with another example. What if we tried to add -2 and -3? Well, -2 is 110. -3 is 101. If we add them together, we get a 1011. And again, because we're in a 3-bit system, we drop that leftmost one, that bold red 1. So we really end up with 011. The real result is 011. You can see in the table it's highlighted. And so again, we can see we made an error because we added two negative numbers. They both start with a binary 1. And we got a positive number, 011, which starts with a 0. So again, the CPU, the processor, it sees this as an overflow, and then it can tell your program, hey, you tried this operation, but you overflowed. Like, you didn't actually have the space you thought you had, and the result doesn't fit. So now we can deal with this properly. There's a lot of advantages to this 2's complement system. Like I said, there's no -0, so zeros always zeros. All zeros, always 0, right? And that's easy because comparison is just very easy because the binary numbers are the same. There's no -0 that you have to special case or anything like that, right? Subtraction becomes the same as adding a number's 2's complement. So if you want, let's say you have the number 16, and you want to subtract 4. Well, you would take 4, and then you would just get the 2's complement of that, and then you would say 16 plus the 2's complement of 4, which is the -4, which is, 16 minus 4, which is what you want to do. You want to do 16 minus 4. Well, you're going to do 16 plus the 2's complement of 4, which is -4, right? And so hardware now only needs to know how to add. It doesn't need a special particular piece of circuit for subtracting. It just needs to know how to add. This is very cool. Hardware can also detect overflow situations very easily and report the errors up. We saw how to do this, right? You add two positive numbers, you get a negative number. You add two negative numbers, you get a positive number. We can tell that very easily, and then the computer can just say that's an error. Okay, well, this is how binary negative numbers are represented in actual computers. They're using a 2's complement system. And the next time, we're going to sort of take a little step back, and we're going to look at sizes in binary, like how much space gets you what. Because now that we know how to represent a positive number and how to represent a negative number, we should know, what sizes get us what number, like what number we can hold in that size in binary. So that's the next lesson. And until then, if you like this video, you should absolutely subscribe. And you can also like our Facebook page to get updates as soon as the episodes come out. And I really recommend you do that. And if you really like our channel, you can also like the video, comment, and subscribe and let us know that you like it. All right, we'll see you next time.